We will now discuss how to calculate wind loads on a truss tower. We will go to the structure type and select truss tower. We go on to MWFRS method next, and we see that the only valid option is Chapter 29, and so that is what we will select. Click on the C and C method, and you will see that there is no method applicable for a tower, so select None. Now we need to decide whether it will be flexible or rigid. You would normally calculate the frequency of the structure outside of our application and then enter it here. If you have not performed a dynamic analysis, you might be able to estimate the frequency using a simplified tool that is within Meca. To use this tool, change the dynamic type to flexible and then click the frequency button. Here, select the method as freestanding lattice tower and then enter the parameters. When you click Save, the estimated frequency will be brought back to the main window. This is a simple rule of thumb and is only meant to give you a rough idea of the frequency. A proper dynamic analysis is always preferred over this rule of thumb estimate. For this example, we will assume a rigid tower. Next, select the Truss Tower tab. The input is a grid, and this allows you to enter one tower section for the entire height, or you can enter multiple different tower sections that are stacked on top of each other. This gives you the flexibility to enter more complex towers. For this example, we will assume that the tower is straight at the top and then tapered at the bottom. We start at the top and work our way down, so first we enter a section that goes from 100 feet down to 75 feet. The section will be assumed to be 40% solid, and so we enter a solidity ratio of 0.4. This represents that the section is 40% solid and 60% open area. This section of the tower is straight and has a width of 10 feet, so we enter 10 feet for the top and bottom width. The shape of the geometry is triangular. The structural members that comprise the tower are round, so we will select the round shape. Now graphically, we can see what we have entered at the right. Now we will enter the tapered section, and so we click the plus sign at the bottom to add another row. The top elevation is 75 feet, because our top section stopped at 75 feet. That value was automatically entered because the program started the next section where the last section left off, because we always work from top to bottom. This will extend down to grade, and so we enter the bottom as 0 feet. We will assume that the solidity ratio of 0.4 is still appropriate for this section as well as the top. The top width is 10 feet, so that it matches the section above. Please note that normally it would match the section above, but it doesn't necessarily have to match. That's why the program allows you to enter whatever width you wish. This section is tapered so that the bottom width is 20 feet. It is also triangular in shape and uses round members. Now we can see a representation of our tower straight at the top and tapered at the bottom. Click Perform Analysis and we get the calculations, which include the wind pressures and shear force for each section. Please notice that we only calculate wind pressures at points where our sections were located, in this case at 100 feet and also 75 feet. The wind pressure does decrease as you get closer to grade. Therefore, if you wanted a more accurate analysis, you could break up the analysis to have more sections so that the wind pressure would be calculated at each section break.